Section 4.2, Least-Squares Regression. This will be a demonstration of number 3 in your Section 4.2 homework, which reads, the scatter diagram for the data set below is shown. Part A, determine the least squares regression line. Part B, graph the least squares regression line on the scatter diagram. And you see here the data set. We have the explanatory variable, the data from the explanatory variable, 0, 2, 4, 4, 6, and 7, and the data for the response variable, y, 7.6, 5, 4.6, 4.1, 3.7, and 1.9. So when we plot that data, we would get a scatter plot. We would get dots that do not form a perfectly straight line. And what we're supposed to find is the least squares regression line, otherwise known as the line of best fit, because this is the line that would best predict what is occurring in the scatter plot. It is the line that best approximates the patterns in the scatter plot. So the values that we would find on this line of best fit, this least squares regression line for part A, would be called the predicted values. Whereas the data in the table that you see here, those are the observed values. That's the actual data. But we can get a line of best fit to make predictions about the scatter plot. Now, the least squares regression line is typically given in slope-intercept form. This is a form that most of you should be familiar with from algebra. The form is y equals mx plus b. That's typically how it is given in algebra texts, where m is the slope being how much the line rises and runs, so how much change in the response variable, y, which is your dependent variable, with respect to your explanatory variable, your x variable, which is the independent variable. That is the slope. And your y-intercept is b. And actually that's the y-coordinate of the y-intercept, where the y-intercept is the point on the y-axis. It's the point that's right on the y-axis, so your x is 0. So the y-intercept would be 0, b, 0, some constant. Okay. So the second box, for the second box in part A, we're looking for a constant. The first box, we're looking for the x coefficient, which is the slope. Now in your text, the form is not y equals mx plus b. It's the same form, but it's written as y equals b sub 1x plus b sub 0. So b sub 1 is your slope, and b sub 0 is your y-intercept, but it's just a matter of notation. In practice, we use software calculator to get the least squares regression line, and that software calculator is going to use yet another form of notation, and then list the slope and the y-intercept. It will tell you the form, what the notation means, and then it will list the slope and the y-intercept. But if you remember, the slope is the x coefficient, and the y-intercept, the y-coordinate of the y-intercept, is the constant. So now let's use the formulas as they are given in your text on page 197 in the purple box. The predictor line y, the predicted response y, is equal to b sub 1, which is your slope, times x, plus b sub 0, which is a constant, that is the y-coordinate of your y-intercept. So here they're giving you the form that they're using. They're telling you the notation for the slope, the x-coefficient, and the notation for the y-intercept, the y-coordinate of the y-intercept. Now let's start with the first formula, slope. The formula for slope is b sub 1 is equal to the R correlation, which you learned about in section 4.1, times the standard deviation of the y values of the response values for the response variable that were given on the second line of the table of the first slide, divided by the standard deviation of the x values for the explanatory variable given on the first line of the table, the data given in the first line. So you would have to find the standard deviation of the y values and of the x values, and also the R correlation. Now let's analyze the slope formula so that you can better see the close connection between the R correlation and the slope of the least squares regression line. Along the regression line, a change in one standard deviation of x corresponds to a change of R standard deviations in y. We have R times the standard deviation of y. So a change in one standard deviation of x corresponds to a change in R standard deviations in y. Now, suppose that R is 1 or negative 1. Recall that means that we have a perfect correlation between the response and explanatory variable. We have a perfectly straight line. It's not a scatter plot, it's a straight line. When this is the case, when the variables are perfectly correlated, the change in the predicted response, y cap, is the same in standard deviation units as the change in x. Now let's look at the formula for the y-intercept. The y-intercept, b sub 0, is equal to the mean of the y values minus b sub 1, which is the slope, times the mean of the x values. So as you can see, we need to use the slope formula first before we can find the y-intercept, because we need the slope to find the y-intercept. We also need the mean of the x values in our table, the explanatory values, and we need the mean of the y values in our table, the values for the response variable. And for the slope formula, we need the standard deviation of the x values, the standard deviation of the y values, and the R correlation of both values. Now, in practice, you would use, again, software or your calculator to compute the least squares regression line, to find the least squares regression line. But I would suggest you do at least this one homework problem with me by hand so that you can better understand what is going on with a least squares regression line and what a least squares regression line is. You already learned in section 4.1 how to compute the R correlation by hand. That was on page 183. So to find the slope, we're going to compute the R correlation using technology. So when we do that, we get minus 0.9538. You also learned how to compute the standard deviation by hand. So for this problem, we're just going to use technology. The standard deviation of the x values given in the table of the first slide, is 2.56. The standard deviation of the y values is 1.867. So I used the data given in the question to find the R correlation, the standard deviation of the x values, and the standard deviation of the y values using technology. So now I have all the values I need to substitute into the slope formula. So I substitute these values where they belong into the slope formula and compute, and I get approximately minus 0.695 for the slope. So this is the slope of our least squares regression line. It's the x coefficient of our least squares regression line. When the regression line is written in the form of y cap is equal to slope times x plus some constant. So then, now that we have our slope, we can calculate the y-intercept of the least squares regression line. Recall the y-intercept is equal to the mean of the y values minus the slope times the mean of the x values. You already know how to calculate mean by hand, so we'll use technology. The mean of the values for the explanatory variable x comes to 3.833 approximately. The mean of the values for the response variable y comes to 4.483. We found the slope on the previous slide to be minus 0.695. So now we have all the values we need to compute the y-intercept of our least squares regression line. We plug them in the formula. One thing you want to be careful with is the fact that the slope is negative. We have a negative slope, a decreasing slope, but we also have a minus sign in the formula. So those two negatives on the first line of our computation become a positive on the next line. And the result comes to 7.147 for the y-intercept of the least squares regression line. So, to summarize, so far we've obtained the slope to be minus 0.695 and the y-intercept to be approximately 7.147. Now please note, in my math lab they would like you to round to 4 decimal places. I've rounded to the nearest 3 decimal places. So the slope would go in the box before the x, that's the x coefficient, and the y-intercept would go in the second box. And there you have the least squares regression line, the equation for the least squares regression line. Y cap is equal to minus 0.695x plus 7.147. Okay, now that we have the equation of the least squares regression line by doing part A, part B asks, graph the least squares regression line on a scatter diagram. And you see here, first of all, your scatter plot indicated with the yellow dots. Those are the observed values, the points obtained from the table given in the question, all of the x, y's of the observed values. So that's the scatter plot. The red line is the graph of the least squares regression line, of the line of best fit. So how did I graph this line? Well, first I used the point that's given in the equation, which is the y-intercept. The y-intercept is approximately 0,7.15. And you can see it graphed with the green dot on the y-axis. That is the y-intercept. So that's the first point. And remember, we only need 2 points to graph a straight line. Now, instead of finding my second line using the slope, which is a decimal and makes it harder to use, I use the fact that every least squares regression line has as one of its points the mean of the x values of the observed data, comma, the mean of the y values of the observed data. And that is the second green point that you see there. We computed both those means when we calculated the y-intercept. So connecting those 2 green dots, we have the least squares regression line. And then I used in the gray that you see here this information about the slope to test that line, to test the slope. The slope is approximately minus 0.7. So as you can see, I start on the red line and I move down 0.7. That's in the minus direction, in the negative direction. And then I move to the right one, the ones in our denominator, rise over run. So the run is +1 because under every number is a 1 in the denominator. So as you can see, when I do that, I land again on the line. So that shows that that is indeed the slope of the least squares regression line. Now, looking at this predictor line, this least squares regression line, you can see that it is indeed the line of best fit, even though this is just a sketch. It passes kind of right through the middle of the scatter plot. It's kind of like the average of those points. And more specifically, what this least square regression line does is it minimizes the difference between the observed values and the predicted values. The observed values are the yellow dots. The predicted values are the points along the red line. Now the distance between the observed value, if you look at one of those dots, and then you go straight up or straight down to the red line, that difference in distance is the error. It's the difference between what we predict and what is actually the case, what we actually observe. We also call it the residual. Now the least squares regression line minimizes the sum of the squares of those errors, the sum of the squares of those residuals. That's the definition of least squares regression line. And among other things, this line shows how responsive the response variable is to changes in the explanatory variable. So the stronger the correlation between the two variables, the more responsive that changes of y values will be in response to the changes in x values. So if there's a cause and effect relationship, if the explanatory variable, we can determine how strong this cause and effect relationship would be. One example of this might be cola consumption versus bone density, where cola consumption is our explanatory variable and bone density is the response variable. And we're exploring a cause and effect relationship, a causal relationship, and we want to know how strong that relationship is, how responsive the bone density is to cola consumption.